design of pre-stressed concrete slabs. So the concepts are the same. You like compression to be positive, is that right? You like compression to be positive. Right. So last time I told you, if you have one way simply supported slab, what we do is we'll have a tendon going like this, supported, and PE is equal to W squared over 8 this E. So for a parabolic cable, W is 8 PE over A squared. So this is going to apply a load from below or upward load like that. And this can be used to compensate for self-weight of the slab. So when you do that, what happens? When you compensate for the self-weight of the slab, and when you compensate for the self-weight of the slab, what happens is slab has delta equals 0 when completed. So deflection due to line has two advantages, and it becomes only the delta due to line and full section effective. In reinforced concrete, full section is not effective because it's a packed section. Whereas in PT, the full section is effective, so it's good in controlling the deflection. So because of that, for PT slabs, we can easily use span over depth, not effective depth of something like 35 to 45. 35 to 40 for simply supported case. And if it is continuous, 40 to 45 continuous. So we actually use this very effectively in one of the projects, and that is the Nigambo hospital project. We had eye girders at 6 feet 8 level. So we cast slabs like this, 90 millimeter thickness, and it had, because it's precast slabs, we had the straight tendons. Those were 5 millimeter wires. So we had another slab here. And what we did was we kept holes like that. And through the hole we welded a bar and bend it like this. So basically we locked the slab with the beam, steel beam. Who is recording? You are recording.
Recording in progress.
You are recording using some software? All right. So basically in this so regarding the slabs, there are so many different options. I'm going to show you one of the concepts that we used. We did a trick in this Nigambo hospital. So we had these eye girders, the universal beams, UB sections. Span is 7.5 meters. And then we had these precast slabs. So we kept holes like this and welded a bar and locked it. Then what we did was we fill this gap with construction route. Construction route. So basically we made sure that the slab is almost continuous, almost continuous. Then we added with some reinforcement, continuous reinforcement, we added 40 millimeter, 40 to 50 millimeter speed. So it can be 40 or 50. So we got a slab with a thickness of only 130. The span over depth ratio was 600.
Recording stopped.
Sorry, Bali, there was a power failure. Can you hear me now? All right, okay, sorry for that. So basically we went for a span over depth ratio of 46. And then they laid an additional layer of, and then did the tiling. So now it's, so the advantages were very rapid construction. Why? Slabs are precast. Slabs are all precast. And steel beams prefabricated. So when you have a portal frame, we need a trick again. So here we use 7.5 meter and had a prop at the ground level. Here we had 15 meters. So we had clear spacing of 50 meters in the upper floor. In the ground floor we had a column. So then the foundations also we went for something like inverted cellular raft type. So what we did was we did not have any shuttering for the foundation. We did not have a shuttering for the foundation. So there is 10, 12, 2022, PT, Slabs. Then, so what we did was we had weak soil conditions, weak soil. So what we did was we laid about 150 to 200 millimeter laterite soil, and this actually helped to make this soil stable. So we could do the excavations like this. So these are the beams on the lines where the columns are located. So in between we just laid the concrete, so all this was quality. So our foundation was quality. The foundation shuttering was quality. So we were able to finish 50 meter by 15 meters of foundation in 1 to 2 days. And then once you have the foundation with the starter bars, so it's a matter of welding a plate to those starters and locate the foundation, locate the column base, and then so you have the column base welded to the reinforcement, and then it's a matter of fixing another plate, and then you can erect it, and then you can grout this way. So this way we were able to get all these erected pretty fast, and then the moment the frame is there, we place the slabs, and then immediately you can place the speed. So we achieved 2 numbers of 50 meter by 15 meter buildings in about 2 weeks, or say 3 weeks. Very fast construction. And then to save time, we actually went with C channels, the core form steel, and then what we did was core form steel. So we made a frame like that. So with this frame, we fitted outside, we fitted zinc alum, inside we fitted Dura panels. Dura panels also we made sure Dura panel also we measure the mounted width 4 millimeter thick cement fiber sheets. Now these days they use the cement fiber sheets manufactured in Sri Lanka by a company called Eltero. So the cement fiber sheets are also manufactured in Sri Lanka. So what is the sheet? The craft paper comes from USA or some other origin. Strong Sri Lankan, fiber sheets Sri Lankan. So is that a very good product? Very strong. And what you have to keep in mind is strong, all in this direction. It's very weak, this direction. So always make sure when you are using a Dura panel, you support it here, support it here, support it here. So if you have a Dura panel on a precast beam, like this third system beam, and support it like this at every 600 millimeters. You can get a pretty strong flow like that, and this can be very cost effective as well. So if anybody is interested in doing the MSc project, already you are selected one, but you find it hard to make it happen, you can try this developing PT, recast, Dura panel composite system. So this is one of the projects you can think of doing, because in the current scenario, the steel is very expensive, concrete is expensive. So with all this expenditure, this type of beams, PT beams, can be pretty cost effective. And if we can load test all these systems with Dura panels, load test it, we can do a very good project. If anybody is interested, you have already selected the project, but you are struggling with it, just think about this type of project, where these are at 0.6 meters. Is that clear, Bhashitan? These are good projects because we need research done on all these different aspects, and we can develop a complete system, because when we are casting these beams, normally we don't do this type of thing where we have just the beam. So now what we do is we actually put some timber pieces like that. So the idea is, once you have the beam done, you can fix a plate here, the timber reaper, like that. And we can have two other reapers, and then mount the flow on that. And then we can have plasterboard. or electro cement fiber sheets. And we can actually create a very nice flooring system with minimum cost, but which looks very strong, which looks like a concrete floor, which looks like a concrete floor. So if you can develop this type of systems, it's ideal in current context because steel is very expensive, concrete is very expensive, formwork is very expensive. These type of systems are also lightweight. Because it's lightweight, even when you are doing a construction in an area where the soil is weak, because the structure is lightweight, you can have a lightweight system floating on the weak soil. So these are all new ideas that you can try. These are the best time to try all these new ideas. So what happens when you go for a continuous slab? We can have a situation where sometimes we can have straight beams and go for a in-situ slab where we'll have the cable going like this. So what happens? In this area, it is forcing up. This area is curving this side, so we are putting the load onto the beam. So you can actually, this total is W, and we can arrange the system so this dumps W by 2, this dumps W by 2. So that is one of the possibilities. So basically, whatever the load that we apply up, we apply downwards over this curve, because when we have a curve this way, the forces are acting upwards. When you put it in the other direction, forces are acting downwards. So this way, this will act as a weightless system, because pre-stress will look after the self-weight. Then whatever the reflection will come only from the live load and the finishers and the services. So you can have a thin slab of span over depth going up to about 40 to 45. Now here, when you have reinforced concrete, we talk about the span of effective. But here we are talking about span or depth, because the full section is there. So you can see when we say the ratio is 45, we are actually talking about reasonably thin slabs. I'd like you to appreciate this particular behavior, because we can make use of it later for designing flat slabs. Now we look at two-way Spanish slabs. So we will establish two-way spanning. We will first look at a simply supported case. So it's two-way spanning. So generally this part of the slab will be loaded more. Because these are supported. So it will span this way, span this way. And when it's spanning this way, you can say WA 8. WA is equal to 8 PE over S squared. In the other direction, you get WB 8 PE over S squared. So if you are, so you might have 60% of the load carried in the short span direction, 40% carried in the long span direction. We really don't know. So the moment you get uncertainty, we have to think about it carefully. We really don't know how much load will be carried in each direction. But we know one thing, that is, in the short span direction, we can carry higher loads. Long span direction, the curve weight is less, so we have to carry less loads. So when you have, so this is a short span. So if it is simply supported, we have the tendons going like this with cover. Maybe 20 millimeters is quite adequate. And then we can make use of wires or strands. So if you are using strands, we can use 12.9 millimeter strands or 15.4 millimeter strands or 15.9 millimeter strands. This gives about 100 millimeter squared. This gives 140 millimeter squared. This gives about 150 millimeters squared. The diameter will not represent the exact area because these are strands. Those are strands, a collection of wires. So we might have a sheet of about 15 millimeter, 20. You see. In the other direction, we'll have another 50. And generally, these will be filled with grease. So this is an unbonded system. It's an unbonded system. So if it is unbonded, in case of a fire, if the tendons lose strength, then you have to have a secondary system. So because of that reason, in the ACI codes, it is recommended to have about 0.2% reinforcement if unbonded tendons are used. Or 0.2% reinforcement. It's not a major amount of reinforcement, but it can be something like these are thin sections. So 1000 into 160 into 0.002. The answer is 320 divided by 78.5. T theta 250, center to center, With 160 millimeters, you can go for 160 divided by 40. 60 multiplied by 40. About 6 meter spans. 6 meter spans. So you say it is about 6.5. About 7 meter spans, you can use 160 millimeters. For 7 meter spans, generally you need about 170, 180 millimeter slab. So here you get 160 millimeter slab or sometimes here. But with 160 millimeters, you need lot of reinforcement like T12 at 150 when the spans are about 7 meters. T12 at 150. You need about T12 at 150. Whereas in this case, you need only about nominal reinforcement T10 at 250. So the substantial saving is T. And you don't need a lot of top seal, only the requirement of top seal. So you can see in PT slabs, you can save concrete, you can save steel, and above all, you can get a slab with lesser deflection. So there are many advantages of going for this. But we have a question. The question is, how we are going to find the PT? So when you have 7 meter by 9 meter slab, so the flat slabs, you might decide to use 160 millimeter slab. So what we do is, we apply about 1 Newton per millimeter square stress in one direction, that is the long direction, and you decide, because shorter direction is good in carrying whatever the remaining load. The shorter direction is good in carrying the load. You are going to carry the remaining load in the shorter span direction. You are going to carry the remaining load in the shorter span direction. So if you are using 160 millimeter slab, so 160.16 into 25. So self weight is 4 kilonewtons per meter squared. The first task is to find how much load that this can carry with a pre-stress of 1 Newton per meter squared in the longer direction. So for that, we have to find the thickness, hour 20. So this is 15, and this is another 15. So the eccentricity in the longitudinal direction will be 80 minus 20 minus 15 minus 15 by 2. How is 20? Minus 20. 50 minus 7. So the eccentricity in this direction is 38 millimeters. It's a longer direction. Eccentricity in a shorter direction is 80 minus 20 minus 15 minus 50. So that is 60, 45, or 15.2. So that is 80, 60. About 52. So you are going to get eccentricities in two different directions. Then we have to see what is the effect of this pre-stress of that is W is equal to P 8 PE over S squared, and that is 8 P is 1 into 1000 into 160. Because we are applying a pre-stress of 1 Newton per millimeter squared. So we are selecting a strip of 1 meter, and eccentricity is 38 divided by 9. Eight newtons so mass is 0.6 8 into 1000 into 160 38 newtons per millimeter. So we are considered 1 meter thick, 1 meter width. So here you get Newton, millimeter, and here millimeter. This Newtons per meter or 0.6 kilonewtons per meter per meter. So basically, if you apply a load of 1 Newton per millimeter squared, stress in the launcher direction, the pre-stress is equal to, the uplifting force is equal to 6 kilonewtons per meter squared. So the total self .0. The total self weight is 4 kilonewtons. So you have to short direction. You have to carry a total of 2.4 kilometers. In the short slide direction, whatever the remainder has to be carried out. Exactly. So in the W is equal to 8 PE over L squared. P is equal to 3.4 multiplied by L squared, that is 6 squared, divided by 8. Eccentricity in the short direction is 52. 52 squared. From this you can find the pre-stress force P. Eight 0.052. I'm just checking the units. 3.4 is in kilonewtons per meter square multiplied by 6 squared divided by 8 divided by 0. So the pre-stress force that you read is 294 kilonewtons per. So now we have a slab that is ready to take the extra load. So we see how to do that. So Basi, shall you take a break and then start? Can you understand this? So basically what we are doing is we are balancing the load. We are trying to find a pre-stress that will carry most of the bending moment of the two-way spanning slab in the short span direction, and still it will carry some load in the long span direction. And the idea is make sure the full weight of the slab is compensated. The full weight of the slab is compensated. That is the concept. Is it clear, Vashika? So in the long span direction, we are being apply a minimum pre-stress of 1. If you want, you can go for 1.2 or 1.3. But the minimum cannot be less than 1. So I apply the minimum force in the long direction. Why? It is less efficient in carrying load. Shorter span direction is more efficient in carrying load. So I'm going to have more force in the shorter span direction. But what are the dimensions? 7 meters. I think this is wrong. This has to be 7 meters. So 7 squared, not 6 squared. So we get 3.4 into 7 squared divided by 8 divided by 0.052. That is 400 kilonewtons per meter. 400 kilonewtons per meter pre-stress. So now you know the pre-stress in both directions. Both directions we provide parabolic cables. We provide parabolic cables. Is that clear, Vashika? So now we have solved only part of the problem. What is the problem? The problem is we have self-weight and we have provided pre-stressing so that self-weight is fully compensated. Fully compensated. That is clear now. Is that clear? Yeah, now we have to apply the weight of finishers as we did for the last time's example. Since this upon case, now we have to apply the finishers, services, and the live load, and then check the stressors. But now we have a problem. Why? This is a two-way spanning slab. If it is two-way spanning, we have to see how much moment will act in the shorter span direction, how much moment will be acting in the longer span direction. So that is what we are going to do next. And once you know the moment in short span and long span direction, what are we going to do? We'll find the stresses due to those, and those stresses should be within the limits, because when you find the stress, that stress has to be suppressed by the pre-stress, axial pre-stress. So we'll take a break and then look into how to calculate the performance of a pre-stress concrete slab spanning 7 meters in one direction, 9 meters in the other direction. So you can see they are fairly strong, long slabs, but we are trying to use a thickness of only 160 millimeters. We are trying to use a thickness of only 160 millimeters. Okay. Bajit, shall we start? Okay. Now, let's say we have a simply supported slab. We apply loads. So we get many moments for simple. But let's look at a continuous slab. So if you have a continuous slab, we can have different support conditions. Something like this. If you take this, these two edges are continuous. If you take this, all four edges are continuous. If you take this, three edges are continuous. If you take this, only one edge is continuous. So you can have different conditions, different support conditions. And to get the maximum moment over the support, we applied the maximum moment over the support occurs when both spans are fully loaded. Right. But if you want to find the bending moment in the span, what shall we do? We load this, we load this. So we go for pattern load. Now when it is fully loaded, what can you say about this support condition? Similar to rotation is almost equal to 0. Why? Because both are loaded. But here, it is not the free rotation, it's not free rotation, but it is on the full restrained rotation as well. That is also not true. So here we consider that it will have about 50% rotation. So if you have, so this is the special condition. So basically, if you have a slab, like that, we consider that the rotation, the moment here will be due to a diagram like this. Because we can get only about 50% rotation allowed. So if you want to find the span section moment, it comes when all are fully loaded. Is the support moment. For the span moment, for dead load, all these will act simultaneously. So again, you get this. For live load, we are going for pattern loading. So you get a different diagram. So we want one set of coefficients for dead, Another set of coefficients for life. So this is what I would like you to appreciate. So we can't get the bending moments directly from one set of coefficients for dead and live loads. For live loads, we have to consider the pattern loading. For dead loads, we don't have to consider pattern loading. For the support, we don't have to consider pattern loading because the maximum bending moment over the support occurs when all the spans are loaded fully. When all the spans are loaded fully. Can you understand this, Bhashita? Right. So, to find, I'll share the screen. So to find those, we have two tables to find the coefficients. Yeah. So these are the tables to find the coefficients, and these are the negative moments, and they can be different support conditions to find these. So for example, this is only these two sides are continuous. Here, these all four sides are continuous. Here you can see only two sides are continuous. Here only these two long edges are continuous. And here only one edge is continuous. So there are different conditions, and I will give all these details. I will find the exact the markings with the clearer diagram. But now let's say when you want to find the bending moment or at the continuous edge, you can use these coefficients. And the coefficient is CA negative W LA span. W is the full load, LA is the span, and CA is the coefficient. And this is a square one. This is square, and these are rectangular ones. And here you can see in the A direction is the shorter direction. Shorter direction, a huge moment is carried. In the longer span direction, a smaller moment is carried. So then we can also look at next one for dead load. Positive moments. These are the sagging moments. Sagging moments in the continuous case, rectangular, the sagging moments are given by a coefficient of 0.036. 0.036. And then you look at the die load case. Here you can see some of these coefficients. For this case is the same. Here you can see 0.036. Here also 0.036 because this is simply supported. This is the simply supported case. This is the continuous case. All four is just continuous. 0.01 is glass slab. But here you can see for the live load we get a higher coefficient. Why? For the live loads we have to consider the pattern load. We have to consider the pattern load. So this way, if you have a continuous slab supported by beams, you can find these coefficients, and these are elastic. These are based on elastic behavior, not the yield line method. So these coefficients are different to the coefficients given in BS811C2. These are different to the coefficients given in BS811C2. They are different. So we see how these can be used, but I will do an example for us in this supported case. So because we are doing the example only for a simply supported case, we will be using only this one. Otherwise, you can use these coefficients as well. But you can see the definite advantage of making it continuous. You can see the coefficients are very different. When it is continuous on all four edges, the moments are nearly half the values. And here you can see when it is continuous, the moments are much lesser than the simply supported case. Bashita, can you see these differences? Right. So now we see how to deal with this particular case where we have a slab of, that is the example we looked at, slab of 9 meters in one direction, simply supported 9 meters this way, 7 meters this way. And we found that the eccentricity in this direction is 52 millimeters. Eccentricity in this direction is 38 millimeters. Right? And we say this subject is an office building. So we have finishers at 0.75 kilonewtons per meter squared. Partitions 150 kilonewtons per meter squared. Live load at live load at 2.5 kilonewtons per. So we'll take this as a dead load, this as a live load. So basically we are looking at this situation, office building having a simply supported case, slab 160 millimeter. The dead load already compensated, and we have selected a pre-stressing of 1000 millimeters, 1 Newton per millimeter squared in the longitudinal direction, and a pre-stress given by a force of 400 kilonewtons per meter in the other direction. 400 kilonewtons per meter in the other direction. Now we want to see whether this would be, what are the stresses that will occur. For that, we have to find the M super dead and M live. To find this, we have to find the ratio between the So I'll share the screen again. So these are negative numbers, but we are considering a simply supported case. So table 1 will not come into the C. Table 1 is not necessary. So we have some dead loads, and here LA over LB ratio. LA is the long side. Sorry, LA is the shortest side. LB is the longest side. So LA over LB ratio is 7 divided by 9. 7 divided by 9. 0.77. So the ratio is 0.77 somewhere here. Ratio is 0.77 in between. So let's find the ratios. This is a dead case, this is a live case. In a dead case, 0.77 means somewhere here, it's a simply supported slab. The coefficients are 0.0585, 0.585, 0.585 this way, and this way 0.22, yes, 0.21, 215. Now we have to look at the continuous case, the live load case. 0.77 gives 0.77 gives 0.5858, 585, 0.585 and 0.216. So the ratios are the same. Why? It's simply supported. Ratios are the same because it's simply supported. So the moments are given by MA positive, MA short span is given by CA WLA squared. So that is 0.58, 0.0585, 0.0585 multiplied by the loads are 3.5, 4.25. LA is 7 squared. So the moment is 0.0585 into 4.25 multiplied by 40. Something like that. 0.9945 kilometers. 0.0585 into 4.25 multiplied by 12.18. 0.0585 multiplied by 4.25 multiplied by 7 squared. Yeah, 12.18. M long is given by 0.0215 multiplied by 4.25 multiplied by 9 squared 215 into 4.25 into 81. 7.4 newtons, kilonewton meters per meter. Kilonewton meters per meter. So if you look at this one, this way we have 160 kilonewtons per meter. This way we have 400 kilonewtons per meter. And self weight, no problem, because already we have looked after that. Now we want to know what's going on with this. Well, 13. Okay. So now we have to see how to see whether the stresses are okay. So what we have to do is we consider short span direction initially. So we have to find the Z value short 16 B H squared 1/6 breadth is 1 meter 0.16 squared. So that is 0.16 squared divided by 6, 0.00427. That is the Z value. In the long span direction also same is it. Then when you calculate MOZ, you get short span direction. M is 12.18 divided by 0.00427, and that gives 12.18 divided by 0.00427. That is 2852 kilonewtons per meter squared, or 2.852 newtons per millimeter squared. Then we have to find POA is 400 divided by 160, 160.16, 10 to the power 3 divided by 160 multiplied by 1000. So that is 400 divided by 160, 2.5 newtons per meter squared. So when you look at all these things, 2.5 newtons per meter squared in the long span direction. So we have 2.5 here, and due to the live load, this compression, we get tension here, compression 2.85, here get 2.85. Minus tension, compression is 5.3. So Bashita, can you see what's going on? So generally a slab can take about tension is 0.36 square root of the grade of concrete. So now you can see why we can use about 30 megapascal concrete, 30 square root of 30 multiplied by 0.36. You get about 1.97. Allowable stress 1.97. So you can make use of 30 megapascal concrete. But if you want, you can go for, if you want a higher durability, you can go for even 37 megapascal concrete. So then we are look at the longest span. So MOZ is 7 point, we calculated at the moment like 7.4 divided by 0.00427, and it comes to 7.4 divided by 0.00427, 1.73 newtons per meter squared. So the axial stress is 1 Newton per millimeter squared, and compression, tension, in the longer direction, you can see there's no big problem. So this is how you will design a slab, a simply supported slab, when you use pre-stressed concrete, where the slab is supported on all four edges. Girahagama, Indrajit, Kumari,
Yes, sir.
Lasita, Mohammed.
Yes, sir.
It's clear. Now, what are the other problems you can encounter? The deflection. We share the screen. So then, how about the deflection? The deflection in a continuous case is given by the rotational case, because due to the dead weight, if it is continuous, the deflection will be almost zero or no deflection. So the deflection will come only from the live load. And so when you consider the deflection, you have to look at the deflection as D 5048 max LB squared DCIC Right. So, there's one example given in the notes, so we can go through the example as well. So, what is the reflection? So, if it is a two-way span slab, the shortest span direction will govern the deflection. So, D is equal to 5 over 48. Moment, maximum moment is 12.18 LB square, L square, 7 square, and the elastic modulus of 30 megapascal concrete can be about 27 kilonewtons per millimeter square multiplied by the IC is equal to 112 B cubed or BH cubed 112 into 1 into 0.16 cubed. So because this is in kilonewton meters, this is in meters, so we have to multiply by this by 10 to the power 6, and the answer of this is 0.16 cubed divided by 12, 0.00341 multiplied by 0.000341. Then the deflection you get the delta deflection in meters, pi divided by 48 into 12.18 multiplied by 49 divided by 37 divided by 0.000341 to the power 6. 0.00675 meters. So you can get a maximum deflection of 6 millimeters. You can get a maximum deflection of 6 millimeters. You can get a maximum deflection of 6 millimeters in this particular slab. Is that clear? Is that clear? So basically span over, so deflection is span over 350, deflection is span over 350. So the deflection allowed is 7,000 divided by 350. 20 millimeter deflection is allowed. You get a maximum deflection of 6 millimeters only. And the span over depth ratio is 160. 43. Span over depth ratio is 43.75. So for a 7 meter slab, we can use 160 millimeters. For 7 meter slab, we can use 160 millimeters. So can you see the advantage of PT? Can you see the advantage of PT? Bashita? So then you have to check the shear. To check shear, we have to find the shear force. For that, we can make use of the last table, coefficients given in the last table. Here you can see between 0.77, you can find the shear coefficient. Coefficient for shear as well. So generally shear is not a major problem because you know slabs, in slabs shear is not a problem. Shear is not a problem. Right? So it will not be a major problem. So this is how you will look at it, because these are supported by the edge. So shear is not a major problem. But you can do the design. So then how we are going to do the reinforcing? If it is unbonded tendons, you will provide 0.2% reinforcement. But it is a bonded tendons, you can provide about 0.1% reinforcement. 0.1% reinforcement. So if it is 0.1% reinforcement, 160,000 multiplied by 160, 0.001 equals 160 millimeters squared. Pi d squared divided by 4 is equal to 3.14 into 8 squared divided by 4. 3.14 into 8 squared divided by 3.14 into 8 squared divided by 4. 50 millimeters. So 50 into 6 into 7,850. Each bar has a weight of 3.4 kilograms, 6 meter bars, and 1000 divided by 2.4. You get about 415 bars per ton. So basically, there is a particular advantage of using 8 millimeter QST bars, because you are going to get 415 bars per ton. And 160 divided by 50, or 60 divided by 50, 3.2, 1000 divided by 3.2 is 300. So you can have T8 bars at 300. T8 bars at 300 centimeters is sufficient to prevent cracking due to any unforeseen problems like shrinkage. So you can cast the slab with T8 bars at 300 center and then apply these loads. On the other hand, if you go with 10 millimeter bars, so you can go for a spacing of about 400 or 450 millimeter centers. You can go up to 500. So it's a very large space. So generally we limit it to about 400 millimeters. And then when you find all this information, now when you are doing the detailing, so in this, generally we know the middle ships will carry higher loads. So some people actually tend to have a lower space in this and then a higher space in this. So in the middle ships, you will apply the total pre-stress, but you will apply little higher pre-stress. You will concentrate the tendons in the middle strip and have less tendons in the edge strip. So that is something that some engineers do, because it will give better ductility. Now let's see how the tendons will come. So 400. So if you are using 100 millimeter wires, each 100 millimeter wire can carry 100 multiplied by 1860 multiplied by 0.7 multiplied by 0.8. This 0.7 is, we stress it to 70% of the breaking load, and this 0.8 is the loss. So each wire can carry 100 into 1860 into 0.7 multiplied by 0.8. So you get 104 kilonewtons being carried by each wire. So if you have 2 wires, the force needed is 160 kilonewtons per meter in this direction. So 160 kilonewtons per meter. So 160 divided by 208. 160 divided by 208. And take 108. So we can have the tendons at 1.3 meters spacing. But the maximum spacing is about 8 times the slab thickness. 8 into 160, 1280. So it's okay. So you can have the tendons at 1.3 meters. 1.3 meters. And the maximum spacing of tendons is 1.5 meters. The maximum spacing of tendons is 1.5 meters. That's the usual way we do it. So in that case, if you have a slab, a washroom that you wish to lower the slab, we generally keep the dropped area to be around 1.5 meters, 1.4 meters, so that on either side we can run the pre-stressing tendons. So we have to plan these drop areas carefully. So in these drop areas, what we do is we have a slab thickness of 160, and if you need about 125 drop, so 125, so you might get only a thin slab of 35 millimeters. So you might have to drop the slab like that. You might have to drop the slab like that. But it's okay to do that with some reinforcement here, and then you'll have some reinforcement to ensure that the slab is properly hung. So you might have to do something like that, and then the pre-stressing tendons will run on the side of the opening. So when you have small openings in PT slabs, you can do this type of arrangement. It will not affect the behavior very much. Locally, you can have drops and then facilitate the drops needed in bathrooms. Facilitate the drops needed in bathrooms. Is that clear, Vashita? Right, okay. So that's another aspect you have to kind of look into. The whole idea of going for these flat slabs is that you can cast them easily. So is it clear? Right. So simply supported or continuous is not a major problem, because now you know even if it is continuous, you can find the bending moment due to line, bending moment due to super dead, bending moment due to dead, or looked after by the PT with load balance. So because of that reason, even if it is continuous, you can design the slab system and supported by a set of beams. Now this might occur in this type of construction where you go for a steel structure and then concrete slabs. But they are PT. You place the shutters and they just cast the slab with fasteners here. The shear connectors can be there. So you can design a continuous slab like that. That's possible. So this is a likely scenario where in a steel building you can consider having a pre-stressed concrete slab. So the beams are running in all directions and you are supporting the slab directly on it. So this is the kind of situation where you can easily use a PT slab of thin section and the floor to floor height can be easily controlled. Is it okay, Bashika? Now we can start flat slabs. That's it. So in the flat slabs, we do not have beams. So generally we have column strips. And when you have a load, we say this load will first be carried this way and then taken this way. And part of that load will be transferred this way, then carried this way. So almost 100% of the load should be carried in each direction. So here you get the load transferred here and carried this way, and then part of the load will be transferred to this column strip and then carried this way. So in each direction, 100% of the load should be carried. In each direction, 100% of the load can be carried. So in the initial times, without much experience, people thought, okay, now we have a column. So ideal thing is, I'm just going just to explain, show you now curved and put it in the other direction. This is not a plan view, this is just clear, make it clear to you, otherwise it's a wrong diagram. I can't draw like this on a plan view. So on the elevation, it goes like this on the elevation. So it is pushing this up, pulling it down. So people thought, okay, what is the best way? Because we get a lot of load transfer here, concentration here, have a concentration there. And few here, few. Bring in the load. So the column strips will be carrying a higher load, middle strips will be carrying a lower load. The deflection also controlled by the longer span, not by the shorter span. So this is what people thought initially. Then they started using it this way, they designed this way. And they said, okay, let's say shorter span carries 60% of the load, longer span carries 40% of the load. No, go for some combination. And with the experience and more testing, they found putting the concentration of reinforcement, the pre-stressing tenders in both directions is not necessary. And no need to consider this type of situation in PT slabs. You can go for a much simpler system. What is that system? Put tenders everywhere, which will do something like this, and put all these loads up and dump it here. So it is one directional load transfer. And then to carry this load, put a concentration of tendons here. Again, going like this. Dump in the whole person. So now what we do is this. It's much easier than putting tenders in all directions with concentration bands, concentrated bands. So we go with this system. We convert the slab to DMS module, dump all the load onto a beam or a column strip, and then put a concentration of tenders in the beam strip so that we can transfer the whole load onto the column strips. So that's how we look at it. That's how we look at it. So what happens is, so it's fairly easy to do the design. So we put these ones, and for the live loads, we apply the loads and find the stressors. With plate elements or shell elements, we can model it with these concentrated supports. And we can find the moments in this direction, or we can find the moments in this direction due to live loads. And we know that there's pre-stress in this direction, and also there's some pre-stress in this direction. Then we can see whether the stressors are okay. So later what we do is, once we decide on the pre-stress, we can model the slab using plate elements and find the stressors and see whether the PT, because the PT is now applied in this direction as well, axial PT. Axial PT is available in this direction also. Whether this PT can carry the effects of live loads. So to do the design, what we do is, first we have to find this system to support the dead load. And once the dead load is supported, we have to find the effect of live load in a slab like this, and then decide whether the stresses are violated, as we did in the simply supported case that we have just set. So first what we do is, we select a thickness, and then we'll arrange a set of cables in this one-way spanning system, and then we will transfer the loads onto the strips, and then we'll provide a concentration of tendons in those strips, and then we can see whether the behavior is okay or not. So that's how we are going to do the design of PT slabs, which are supported by columns only. Columns only. Is that clear, Bashir? So basically, we are converting the two-way slab system to a one-way system. Because it's a flat slab, which is supposed to span in both directions. But in the case of PT slabs, we simply convert it to a one-way system, where the load transfer takes place only in one direction. And then we check the stresses. Okay. So we see how this can be done. So basically, we can have this two-way system or one-way system. And what we prefer is this one-way system these days. So what we can do is, first we compensate for the dead weight of the structure, and then we see the live loads and see whether the live load stresses are okay or not. Right? And then we'll dump all these forces and then see whether the stress violations can occur. And then we'll provide some additional reinforcement as well, so that the slab will behave in a proper manner. Okay? So what we do is, we take a break and then have a look. Okay? Bashita, shall we take a break? Basically, now when we have a two-way spanning slab like this, we convert it to a one-way system. So that means we are trying to, so we select the thickness. So generally we select a thickness of about 8 millimeter, 200 millimeters. So let's say we have a span of 8 meters this way. We have a span of 7 meters this way. 8 meters this way. So what we do is, we have a support here, support here, support here. Now we have to think about we say the distance to the centroid will be 30 millimeters. Because we have a finite size for the tendon also. So let's say we allow 30 millimeters to the centroid of the tendon. So that means we have an upper boundary here. And this is, then we have 70 millimeters here. And then we also need a curve going this way. So we say that, over 0.5 here, 0.5 here. Going this way. So now we have to think about this. So here you have 70 millimeters. So we can think that we are going to get about 50 millimeters up to here, and then it's going to go on a reverse curve. It's going to go in a reverse curve. Right? So if we now we have to balance 0.2 into 25, 0.2 into 25 is 5. So let's say we are going to balance 80% of that. 80%. That means we are going to balance 4 kilonewtons per meter square. Generally, we don't try to balance 100%. There's a reason for that. You will understand the reason in a moment, because if you try to balance 100%, some places it might balance more than 100%. Even that is okay, because some people like Australians actually go for that system. But in this example, we try to balance 80% and see what happens. So sometimes, you have to do few adjustments later. So now we can see this is 7 meters. So this is 6.5 meters. Over 6.5 meters, we are going to get an eccentricity of how much? So 6.5 meters, here you get 50, here you get 30, halfway through you get 25, and 70, so you get an eccentricity of 95 millimeters here. And here you get an eccentricity of 50 plus 70 here, eccentricity of 120 millimeters here. Is that clear, Bashita? Here we are keeping something extra, okay? Now, what we want? W 8 P E over L squared. OP is equal to W squared over 8 E. So let's find the pre-stressing force P over 1 meter width. P is equal to W is 4, L is 6.5 squared, this is 6.5 meters, divided by 8 into 0.095. This will give the value of P. 4 multiplied by 6.5 squared divided by 8 divided by 0.095. 222 kilometers. Then we look at here, P is equal to so we'll consider this P and then see, we look at how much W we are uplifting. 8 P is 222 into E is 0.12 divided by L squared. Solar squared. 8 into 202 into 0.12. divided by 39. So it's going to balance 4.35 kilonewtons per meter. So can you see why I didn't go for 90%? Why I didn't go for 90%? So I could have gone for 90%, but I have gone for 80%. So I balanced 4 kilonewtons and found the pre-stress has to be about 122 kilonewtons per meter. And then I found how much I am balancing over this distance. So I am balancing 4.35 kilonewtons per meter square. So we have to now look at the situation. So here we have a beam. Seven meters, 8 meters. So here we get 4. Here we get 4.34. Balanced. Right. Now, what is the total force here? 4 into 6.5. The total force is 4 into 6.5, 26. And the total force here is 4.34 into 7. 28. Four point 34 into 7, 30.4. So what is the idea? You have to dump all this force over this distance. So if you take the average of these two, average is 26 plus 30.4 divided by 2. So we get about 28.2 kilonewtons. So we want to dump 28.2 over 1 meter length. So W is 28.2. Now speed of P, W is equal to 8 PE over L squared. So from this you can find E when W L squared over 8P, and E is equal to W is about 28.2, and L squared is 1 squared divided by 8. P is 222. From this one you get 28.2 divided by 8 divided by 220. 0.0158. So that means when we is going this way, we need to have an extensity of about 16 millimeters. So it has to go fairly flat in that region, and the over 1 meter it has to reverse its direction. Because it's reversing its direction over 1 meter with a small extensity of 15.8, it can exert a big force onto the column strip, and that is the force that we expect from both sides. So the idea is the cable will gather the load in the span and put it onto the support. Put it onto the support. So that's the idea. So what we have to see is that we keep eccentricity of 16 millimeters, then we are reasonably okay. So what we are doing is we are getting the load from here and we are putting it back onto the cable. And the concentrated cable should be designed for a load of 28.2 kilonewtons per meter. The concentrated cable should be designed for a force of 28.2 kilonewtons per meter. So in this direction, for 1 meter, we get a load of 28.2 kilonewtons per meter. And we are designed for that particular load. So now what we have to do is, now we are balancing about 80% of the load. Now we have to see what will happen when the live load sets. So let's say we are having finishers 0.5 kilonewtons per meter squared, and we'll have partitions 1, and we have a live load of 2.5 kilonewtons per meter. And in addition to that, we have a remaining part of dead load, that is 1 kilonewton per. So because we balance only 4 kilonewtons per meter squared, so we have a balanced portion of about 1 kilonewton per meter squared. So what we do is, now we'll apply these loads. And see what the type of bending moments that we get. So here we apply 3.55, about 6 kilonewtons per meter squared. So if you apply 6 kilonewtons per meter squared, this area, we can get a bending moment diagram. So what we have to do is, we have to use SAP 2000 and analyze it, get the bending moment diagram, and because we are applying 222 kilonewtons per meter pre-stress, we know the pre-stress, and we have a continuous bending moment diagram. We can find the bending moment here and bending moment there, so that is not a problem. So we find these bending moments for a load of about 6 kilonewtons per meter here, and here you will get a load of 5 minus 4.34 is equal to 0.6866. So here you get 3.54 to 3.54. So this is 5. Here you get 4.66 kilonewtons per meter acting in this direction, this distance. So we apply these forces, and then what you do is you see whether find the moment, find MOVZ plus pre-stress, and see what are the stresses. See what are the stresses as we have done earlier. And if you think the stress is little, stress is too much, say we get the allowable stress is 2.5. Here you get 4. What shall we do? That means we are having some extra stress than what we can actually resist. So what we can do is we can provide some additional reinforcement. So the additional reinforcement will be, we find the area of this diagram. From that we can find how much tension will act, and for that tension we'll provide some reinforcement. So that's what we generally do, because when you do a flat slab design, sometimes what happens is you'll find when you compensate the dead weight and provide pre-stress, that pre-stress cannot suppress all the loads, all the stresses due to live loads. And then at some locations you might need a little bit of reinforcement. And the amount of reinforcement, how you find the reinforcement is, you find what is the stress that will occur in the tension zone. And when you know the stress, you can always find the force. Force is given by stress is sigma multiplied by the half the side x, and so you find x multiplied by 0.5 will give the force, and for that force you have to provide reinforcement. So that's what we generally do in pre-stress concrete flat slabs. So it's a fairly straightforward task. First task is select a system like this, make it one-way spanning, and then what you do is you will make sure there are some upward forces. Those upward forces can be transferred over a short distance as a band, and then you will find the pre-stress needed in the tender cables per meter width. And once you find the pre-stress needed per meter width, we can work out the curvature that we need over the support. So that will give us almost a flat plate, and then what we do is we can apply the loads, the live loads, and then get a bending moment diagram. From that bending moment and the pre-stress that is available, you can work out the stress range. If the stresses are too much, then you can provide some reinforcement. If the stresses are within the limits, you don't have to do anything. The slab will behave well. Is that clear, Bashita? The same method, right? Only thing is you have to use SAP 2000 and get a bending moment diagram for this, because these are the loads that we lacked, and we don't have to worry about this portion because the loads on this portion are already taken into account in the other direction. Because we have a band that can take account of whatever the load acting in that particular band. That's clear. So we can have a band of about 1 meter width to have a concentration of cables. So in the band, now you have to design the band with we got 8 meter spans in that direction. So you get 8 meter spans, 200 millimeter slab. So you can start like this. And here you have to be careful because here you get some clash with this. So if I have to adjust, ensure that those bands will not go through this. Because the requirement is when you have a column, you have to ensure about two ducts go through the column. When you have a column, you have to ensure about 2 ducts go through the column. The idea is in case of an emergency, this band that's going through will act as a tie and prevent the collapse of the track slab. And now we have this band, and other tenders can be outside or 1 meter. And again the same concept. And you have to see all these forces are brought up to the column and dumped over the column. So because they are dumped over the column, now we have to make sure we have the column. So we need some reinforcement continuing 0.3 L this way. So we provide some reinforcement this way also. And we provide some 16 millimeter bars generally over 0.3 meters. So what are the advantages of providing bars like this is it can increase the shear capacity of the slab. And using the same principle, now here we know we have to balance 28.2 to 30. That's the range. So what we have to do is we have to provide P8. P is equal to W squared over 8. W is 28.2. And if you know the eccentricity in this direction, again, let's say the eccentricity is about 90 millimeters. Eccentricity is about is 95 millimeters. So let's say is 95 millimeters. And from this, you can find the value of P. P is equal to 28.2 into these 8 meters. So let's say we go for little longer reverse curve here, something like 7 meters here, 7 squared. divide by 8. Eccentricity is about 95, 0.095 multiplied by 8. From that, you can find the distressing force needed, 28.2 multiplied by 49 divided by 0.095 divided by 8. So you get 1880. So with this information, now we can tell about the pre-stressing system that is needed. But these are little approximate calculations because there can be few variations here and there. So this way, we know pre-stress force is 220 kilonewtons per meter. And over this width, we need a lot of pre-stress and we need 1880 kilonewtons per meter. And we can provide half of that here, about 900 kilonewtons per meter. So we provide some reinforcement, 1818 kilonewtons per meter. And this way we have this 120. So we have effectively created a one-way slab. Effectively created a one-way slab supported by bands of beams. Can you understand this, Bashika? So once you decide on the pre-stressing force like this, you might need some extra reinforcement in these regions, in that direction, and here also in that direction. And you might provide some distribution reinforcement in the other direction. So that will all depend on the stress diagram like this. So this may be about 5, this may be about 4, this may be about 7, this may be about 4. And if the allowable is 2, that is exceeded, which means the section is cracked. From this you can find the depth of this one, and from that you can find the force end. Is equal to 0.5 into y into 4.0 into the width 1000, and n is equal to 0.87 fy area of reinforcement. From this we can find how much extra reinforcement is needed, and we provide that reinforcement. So this is the method that is practiced by Americans. Americans use this method. The advantage is the slab will remain flat after tension, almost flat. And you can even balance up to 90%. So I started with 80% to ensure that nothing goes wrong. And then if these stresses are violated, then you can try 90% balancing. Balancing 90% of the dead weight also can be tried. Balancing 90% of the dead weight also can be tried. So the advantage is we are removing the effect of dead load by using a curved tendon. And then we go for axial pre-stress and see whether the stresses are violated. If the stresses are violated, it will be only in tension, not in compression. So if the stresses in tension are violated, we can provide some extra reinforcement. So this way, you can have a flat slab with minimum reinforcement. And in addition to that, we will provide 0.1% reinforcement in both directions. Something like T8 at 300 cm in both directions. In addition to that, you need some 16 millimeter bars over the support in both directions. Generally, we provide T16 at 150 cm to center over a length of 0.3 meters, over a length of 0.3 times the span, 0.3 times the span. So that is the usual detail. T16 at T16 at 150 center to center over about 0.3. So that's how we provide some reinforcement over support at the column, and that will enhance the shear carrying capacity of the slab. But when you look at this, one thing you can see is this particular type of construction is not very suitable for our Sri Lankan type scenario, because we always try to use heavy partition walls. But if you go to other countries, they don't use heavy partition walls, they use dry walls, like lightweight walls. And these lightweight walls are just a timber frame, and on both sides you get plasterboard. You get plasterboard on both sides. So you get sound insulation and a very lightweight partition wall. The reason is, higher the load you put, extra load you put should be carried by using extra reinforcement. The whole idea is we are compensating for the self-weight of the slab by using PT, and then we apply the loads and see if the loads are very light, there is a perfect system, because once you suppress the dead weight, the slab will become axially loaded panel, no cracks, so the deflections will be small. But in addition to that, you have to see that the stresses are not violated in the sections, and it's effectively a one-way system. And if the stresses are violated, then you have to provide some extra reinforcement to carry those additional stresses. Is that clear, Bashika? So that's how you will design a two-way spanning slab. And the method is approximate. Because there's pre-stress, what will happen? We are stressing a cable which can carry 1860 only up to 0.7 multiplied by 0.8. 56%. Only up to about 1860 multiplied by 0.56, 1050. So what is the margin here? Margin is 1000, it's about 800. Now what happens in reinforced concrete? We have 500 capacity. We go for 0.87. We had 434. Even under service conditions, we can go up to 434. So the behavior wise, here you have only a small margin, here you have a huge margin. So what's the way that the flat slab can fail if it ever fails? It can fail only due to what? It can fail only due to it can only fail only due to what? Shear failure. It can fail only due to shear failure. Why? Because when you consider flexural failure, it has a lot of capacity. It has a lot of capacity. What is the reason? We are here and we can go up to this level. at altitude. And then the section can crack and it can carry load in altitude. So altitude is not a major problem. Altitude is not a major problem. You can check and see how it behaves in ultimate capacity. But shear is a problem. So that's why in some countries, rather than using reinforcement, they put some steel sections like that. Steel. And it's called a shear head. So element steel and make sure the flat slab does not fail. Flat slab does not fail. So there are improvements that people have done. So that's why once you do your PT design for a slab, you will send it to the specialized PT company. And they will check and say whether it's okay because they have software that can check for all the conditions. So what you do is you will do this kind of approximate calculation, come up with a reasonable tendon system, and then see the reinforcement needed for stress violations, and then you should submit it to the specialized PT company, and they will check and tell whether you need any adjustment to your design. So that's the usual practice because, you know, to do manual calculation, it's not that easy, but you can do a reasonable manual calculation unless you have to go for a software that can do it, because in software you can do various things that are difficult to perform manually. So the usual practice is you'll try to understand the behavior and convert it to a one-way slab system and calculate the amount of load balance like this. Check the stresses. If the stresses are too much due to live loads and other permanent loads, then put some reinforcement at the locations which are needed, and then you will prepare a drawing and then send it to the PT company and get it checked by the PT company, because they generally give that service as part of you purchasing their pre-stressing system for construction. So they provide that facility because they have the sophisticated software that can check the system. Is that clear, Bashika? So this is how you have to look at the fat slabs. So you can do reasonable calculations. They are not 100% accurate, but you can see the concept. And concept is, you know, we try to convert it to a one-way system, and using load balancing, we try to see how much load that we have balanced. Based on that, we can even go up to about 90-95% balancing of the dead weight. And once the dead weight is balanced, we know the axial pre-stress. And based on axial, then we also know the amount of loads that are applied due to live loads. And for that case, we can get a bending moment diagram by analyzing a one-way slab, one-way beam, we can just analyze a beam by using SAP 2000, get the bending moment, diagram. From that, you know the bending moments in the span, and check for the span moments, the stresses. And if the stresses are satisfactory, then you don't have to worry. If the stresses are violated, then we consider anything below the neutral axis is cracked, and all that cracked, the force in that cracked concrete should be carried by using reinforcement. And then we call it extra reinforcement. Then the system will behave well. And in addition to that, we can find the tendon profile in the bands as well. And after doing all that, you have to do a shear check and see whether the slab can be subjected to shear failure. So because flat slabs can fail in shear, especially under earthquakes. So it's a good practice to make sure the columns are large. So what happens when the columns are large? When you have a large column, the critical section will come around it at a distance d away, and also you can get punchy shear perimeters. And all these critical perimeters will have a sufficient length. If the length is more, stress is force divided by area, where area is length multiplied by thickness. So this way, you can ensure that the flat slabs behave perfectly well. So in a flat slab building, do not try to shrink the columns and make them small. You can have large columns, and the large columns are particularly advantageous. Is that clear, Bashita? Right. So with that, shall we end? And is today the last lecture? Bashita, do you know whether today is the last lecture? Only thing is I have covered what I wanted to cover. So you would better check with Dr. Bhaskar whether he needs any extra time or whatever. And also regarding the assignment, I told you what to do. We have to design a beam, a continuous beam with the spreadsheet, and then find a tendon profile and show that all those stresses are okay. But only thing is, don't use the spans that are given in the spreadsheet. You can go for different spans, and also the sign convention in the spreadsheet I have given is different, but the answers are the same. So you can convert it to compression positive and tension positive. Okay, Bashita? Right. Anything else? You want to get any clarification or any point that is not clear? No more problems. Then shall I end the lecture? Bashita, can you share this with Imanta? Okay. Then we can put it on the YouTube as well. Okay. Right. So I'll end it there. So raise hand. No, not raise hand. Chat. No, nothing on the chat. Okay, so I'll end it there. Okay. Thank you.